What's up, guys? Welcome to the PPO implementation. Last video I covered actor, critic, and PPO, and in this video I'm going to implement it in JAX. And I've progressed a lot in how I code using JAX, so you're going to see more of the actual loops and the actual structure that JAX code is supposed to have. And at the same time, I hope this serves as a way to kind of open up your understanding of PPO. It certainly was for me when I implemented it. So let's just jump straight into it. I'm gonna code just a small bit of it, not too ambitious in scope, because we have another video coming up where we cover reinforcement learning from human feedback, and that I also implemented it from scratch. That video is going to be a lot more ambitious than this, but here we're just going to test it out on a CartPole environment and make sure we understand each step-by-step process of PPO. So, let's just make a PPO.py. That's going to be the first thing we're going to code up. And we have to understand the functional nature of JAX. So I'm going to start from like the wider scope. Basically the function that trains all of the epoch or all of the episodes that we're going to be working with, right? And then from there, I guess we'll kind of dissect and just pry deeper into the actual algorithm. And hopefully by the end of this video, we'll have a fully functioning implementation. But the first thing I want to start off with is a function that trains all of the episodes. This function essentially is like the overarching training loop. Since this is a small example, just using CartPole, there's not much like logging and tracking that I want to do. So I'll just not focus that much on that and not make like a train function where, we have print statements and 1B logging, things like that. Here I just want to keep it as pure JAX as possible. We're just going to have a train all episodes function. And inside of each function here, when we train all episodes, this is basically going to be the whole process of PPO. So if we remember from last video, PPO had a couple of distinct steps. Now, I wish I'm going to figure it out for future videos, how I could just write on like on the computer or something, because I don't want to be switching back and forth between my computer and iPad, which would require me recording on Google Meets. That's not something I want to do. But if you guys remember, the way that PPO works is that it rolls out multiple steps up to a certain point. Let's call it n steps. And then from there, we actually perform the updates that we want for k amount of epochs, which is separate from epochs, as if you think about it in supervised learning, how an epoch is when you cover the whole data set. In this case, the epoch will be the amount of times we actually update using PPO. And that's basically the whole point of this function here. We want to do the whole part from the rollout to the updates, right? And then just do that a bunch of times. This is our final training loop, basically. But this means that we have to have a separate function, right, for the actual rollout and then for the actual updates. And so let's leave this function here for now, and let's make a function for rewards, or sorry, not rewards, rollout, and also another function for the updates. Now, normally in JAX, when we want to do our updates, we actually split that into two. We do the train step, which is one step, and then we do multiple runs of that. And so I'm going to separate here. Let's leave a function. Here's for the updates. More importantly than that, it would be the train step function that would allow us to do that, to where we actually do the updates in JAX. And now I want to start off with probably the easiest bit, or actually just for understanding purposes, let's go in order, right? Let's go with the rollout. And let's think about the rollout, right? What exactly we do in the rollout. So the whole rollout, as I said, it's steps. You take your steps and you collect your data. That's the whole point of the rollout, right? Take steps in environment, collect, well, environment, and collect data. We have to think about what the data that we're actually collecting is, right? This also, I'm pretty sure in PPO we refer to it as the buffer. Buffer would be kind of like the data collected. It serves as a memory for the actual algorithm, I guess. Something that isn't the case in actor critic or reinforce, because there is no point for a memory when we go step by step, step update. Here we're taking a bunch of steps, so we collect all the data for that step and then we go through, right? And if you remember, some of the data that we have to collect is the like the return / reward, right? For that step or for that rollout specifically. We have to collect the value, right? The value that is basically generated by our critic. And in the same function, well, yeah, that's basically two of the more important things that we have to collect. We have to collect also for future computations, we have to collect the log probabilities of the policy's actions, or not policy in this case, but when I refer to the policy, let's make this distinction up here. The policy is the same thing as the actor, and the value here is the same thing as the critic. Let's just have that clear. I think I'm just going to name them actor and critic anyways, but log probs. And yeah, for now, let's leave it at that. So in JAX, when we loop, the smartest thing to do is to kind of avoid Python for loops, Python while loops, anything Python related, print statements, all that. It's good to throw that out the window, right? We have to have something that can compile to XLA. And that is why here we have internal loops, and JAX has its own looping functions and looping mechanisms that we have to look at. And that involves the use of a carry, right? Carry, since this is a functional language, whatever we pass into a function has to kind of cleanly travel through. Try to think about it philosophically in that case. So let's create like an initial carry, and let's call it init carry. These are basically the things that we are gonna like pass through our loop itself. Now, normally we have in reinforcement learning, we have and we keep track of the observations and the like environmental state. So what we're gonna pass through is our initial observation and our initial state of the environment. And basically, every step that we take, this gets updated to the current or to the next environment state, next environment observation. So far, so good like that. And then basically what we end with is a final carry, which would contain the final observation, final environmental state. Basically, everything that was passed through this carry will return in its updated form, right? And so this is the first thing that gets returned from our loop. Let's actually just name it as the final carry. And remember what I talked about, the buffer. This is the actual data that we collected. Let's just call it buffer. And what we are using here is what we call jax.lax, and that module contains a lot of specific looping mechanisms for jax. So let's just import a couple of dependencies that we need. And let's do Flax for just in case for now. And yeah, should be good with what we have. And yeah, let's go straight into this part right here. As I said, jax.lax, and we'll use jax.lax.scan. This basically loops through a function, and it keeps collecting the returns of the function, which, as you know, is very important for us. If we want the return, not like the Python return, like if we want this return for reinforcement learning, we want the total accumulated reward at the end. We want to collect the reward at each and every step, right? Same thing with the values. So it's important for us to be able to keep track of all of these things. And that is why we have, that's why we'll use jax.lax.scan. And what we pass through here is a body function. Basically, that function is where all of the actual data collection will occur, and where each step will take. And that means that we'll kind of define it here, a body function. It's an inner function. And for now, let's just pass it through. But we'll use that function, pass that function through, right? And then this function, it will have a carry as its input. And so we'll pass the body function, right? We'll also pass the initial carry. And also, we want to know what the length of this would be for. So we're also going to pass none here. Reason being, here we are going to, I'm going to just write this down. We're going to return the carry, but we're also going to return the buffer. Now, the buffer is not going to be needed for the future steps, right? So we'll just leave this blank right here, but we're going to have to initialize it as none since we don't have any memory right now. And as I said before, we're also going to have to define the length. And the length will be, like I showed here, let's just call it n steps. Let's go back up here, define our n steps. For now, let's do 128. We're going to use CartPole, so 500 is the max turns for CartPole. We're going to do 128, right? We're not going to roll out the full environment. We're going to just roll out up to a little bit. 128, relatively arbitrary. And yeah, so again, we are going to, with this function, we're going to pass the initial carry, and we're going to pass a none, which gets returned as the buffer. This means that it still gets saved, although we don't use it in the next iteration of the body function. It still gets saved up to the point where we have our buffer here after this loop, loops through for n number of steps. And so let's build out this function now, right? So again, here we have our initial carry, which is our observation and our environmental state. So we want to unpack this carry, right? And we'll just call it obs and end state is equal to carry, right? Because that's the tuple that we're unpacking. Let's just say unpacking carry. Think about it as like, think of carry as like the messenger that takes or that carries a lot of information that we need inside of it. And so first thing we want to do is we want to sample the actor. Now, right now we don't have an actor model initialized yet, but let's kind of pretend that we do. And let's return the action and the log probabilities. We're going to work on this after, right? But the model that I'm thinking of using is going to be very similar to what we used in the reinforce video. Almost the same structure, but we're going to have a sample, an actor.sample function, and that function passes the observation as well as the key. We're going to leave this here like this. We also have to manage the state of the keys, right? Of the random number generator. But how exactly do we do that, right? As you know, in JAX, we have to kind of split the keys for each specific thing that we do. Otherwise, the same numbers will get generated. So it's also important for us to have that in our carry, right? We're going to pass a specific RNG through our carry, right? And then for each thing that we do, we are going to, I guess in this case, I'll just call it RNG action. We are going to jax.random.split that key and basically make a new key out of the original parent key. You could kind of think about it as splitting it in some tree type of way. And you make sure to do that every time that you need a key for a different action. Make sure to always split that key into something different. So here we're going to take the action, right? And this API of the sample, that's just taken from my reinforced implementation. You could either watch the first video or just skip ahead. We're going to make the model anyways. And here we pass the RNG action. This is basically given an observation. Let's output a distribution and generate an action from it. And we're also going to generate the log probabilities. Remember, the log probabilities get saved. So it's very important. And not just do we do that, we also estimate a value from the critic. Now the critic, what basically does is that given that state, it estimates a value. You can think of the value as basically like a prediction of how good that state is. And what we do with that is we generate an advantage, right? Yeah, we generate an advantage. And we'll cover this more later, right? So here what we do is we have our critic generate a value given the observation, right? Again, we haven't defined critic, but as you remember, we have a two model architecture here, or two model algorithm here. So we'll define it later in a models.py. But for now, let's just leave it. Value passes through the critic. So now what? We have the action that's taken. We have the log probability of the action space, and then we have the specific value that the critic generates. Next step here is we want to actually take a step in the environment. So take an environmental step. And so how this works, oh, and I forgot to mention, probably very important, we're going to be using gymnax, which is kind of like OpenAI's Gymnasium, but it is compatible with JAX, which allows us to actually make the most of the of all of the benefits that JAX brings us. And so let's take an environmental step. The way this is done in the API is just we do env.step, and we take, here there's another key, right? Here there's a key, but here we pass this current state, we pass the action that we take, and then we pass the parameters of the environment. Now these env params are actually generated when we make the environment. So let's make sure we do that, right? Environment. We are going to have our env and our env params, and that's what's returned when we do gymnax.make the environment that we're going to use. Here in this case, we're going to use CartPole v1. And so we pass those parameters through. And again, you saw how I said we need a key here. That means let's split another key off this. Now we can do it in the same line. Here we just do RNG sample, or RNG step, I guess it would be in this case. And here what we do is we split into three. Make sure to kind of denote that we're splitting RNG into three. The parent and then the two children. In this case, RNG step. And so what this step function returns is a new observation given a new environmental state. we're going to save these, right? We're also given the reward for the specific step that's taken and a done function. So also return something else, but it's not really important for us. What's important for us is this done and then the updates to the environment. Now this done tells us whether it's done, like whether the environment reached an ending point or not. And we're going to use this to basically have it in the memory, right? So here we're going to save the carry, right? The new carry. Carry is going to be the same size as this, but now we have, we have a new one, and we keep the same RNG. We pass it towards the future, the new end state, and then we keep the same RNG. That gets passed to the next iteration. And then our memory, what we'll call our buffer, is going to contain our observation, our action, our reward, our done, our log probabilities, and our values. Basically, everything that's important for this step. Now, you saw the data collected, value, log probs, and the reward, the return. The return will be calculated throughout the reward. And yeah, that's pretty much this rollout function. We generate an action and a value, and then we take a step in that environment, collect the reward, and we pass it on to the next one, to the next step. And now here we're going to want to unpack the final carry. What does the final carry have? It has these things, right? So we just put final observation, final environmental state, and just the same RNG. We unpack it from the final carry, and then we do the same thing with the buffer, right? We unpack it. So we have the obs, the actions, the rewards, the dones, the old log probs. Each step is saved, right? And then we have the values, and we just unpack this from the buffer. And this is going to be helpful for us in the future. But we know now, with this information, we're going to have to collect, we're going to have to compute the advantage. The advantage, as you know, is how much better things turned out than the average. This was the advantage. It's denoted by that equation. It would be like the actual reward, or I guess return, minus what the critic predicted. And that basically tells us if what we did was better than average or worse than average. And to do this, we have to kind of compute the GAE. Here. So given the GAE, what we have to calculate, something I have to go back on, is we have to calculate the next value. I kind of forgot that. And we make a function called compute the generalized advantage estimation. We pass rewards, values, dones, and next value. What the dones is just like I was saying here, it's a 1 if the environment is just finished, or a 0 if we can continue. That masking is important as we calculate the rewards and the advantages. But yeah, the returns will be the advantages and the return. And so the whoops. Oh. And so the GAE, the generalized advantage estimation, or even better yet, let's just go to the paper, right? The PPO paper. Here, I don't know why it's so zoomed in. Where are we? We are basically calculating this. And it's just like equation stuff. But it's literally just copying these this equation so that we can calculate the advantages. Now, as you can see, this is recursive in a way, right? We have to do it at each time step. And so again, you know, Jax doesn't like for loops. So we're going to have to lax.scan once more. But the first thing we want to do is the first thing we'd want to do is calculate the this right here, which is the delta. Now this delta is calculating the reward at time step t plus gamma with times like the next value. So this is why we need that next value, right? So we can calculate and compute the delta minus the predicted value for the current time step. And this gamma, if you remember, it's kind of like our discount factor. As we go into the future, the rewards should be valued less. And so let's start with this part right here. Yeah, since these are all NumPy arrays, we can compute everything at once for the deltas. But first thing we have to do is we have to make a new array for the next values. This is basically just appending this next value to. So from the first index forward, right? Because the 0th value should be 0, I think. Might be mistaken there actually. Yeah, since we're computing the next steps, hold on, then the current one shouldn't be. We're like ignoring the first index or the 0th index, right? We're just basically, this tells us if values is like 1, 2, 3, what we're doing is, and the next values equals 4, then what we're doing is we're shifting, we're saving 1, 2, we're shifting 2 and 3, and then we're appending 4. So we keep the same length, right? We have to do this to keep the same length. So that means that the values is always one step behind, which is why we even have to compute the next value in the first place. Honestly, I don't have that too clear right now. Now I'm a little confused. Let's walk through it for real. And we append the next value to that. And then let's calculate the deltas. So the deltas is literally calculating, like I said, the rewards plus I see. I'll tell you guys exactly what's going on. First, we have to multiply by the gamma. You saw right here. By the way, this red screen is for whenever I mess up and get super stuck. It makes it easier for me to edit. All right. Where are we? The gamma times the next values. Whoa, next values minus the values itself. Right. And then we also have to compute like the actual mask part of it. So let's just do 1 minus duns here, which would turn this to 0 if the environment was done. Now, here's why. The 0th index doesn't matter since we're talking about the future values. Now, that's why we need a next value in the first place, because if you could think about it, we can't compute the future value of the last step, right? We have to explicitly do it. And that's why here, if values was 1, 2, 3, 4, 5, that means that next values, it basically tells you the future, right? it's 2, 3, 4, 5, 6. And that's basically what we did. So we're doing, for every step here, we're kind of discounting the future and with the gamma and then subtracting it from the current step. Hope that made sense. I guess I'll keep it here. Now that just computes the deltas, right? Now let's see the other part of this. This is the equation that we're kind of making. So you see, deltas is an array right now. And we start off with the current deltas. We add the gamma times lambda. If you remember, the lambda kind of dealt with the variance of this advantage computation. And we multiply it with the next step of the delta. And we do that all the way till the last delta. And that's how we compute the advantage. Since it's like adding one to the next, right? We can low-key, and since we have to go backwards on it, we can do this using a lax.scan. So if you think about it, reverse like scan. We do a jax.lax.scan of some function, some body function, and we start with an advantage of 0, right? And some carry, or not some carry, but some value we pass through here. And we do this all the way till it's done, and we do this in reverse. Now, what should be returned from this? Again, we're doing the advantage. Now, if you remember, a carry gets returned along with a specific value. In this case, we're going to just keep the advantage. We don't care about the carry that much. Actually, in this case, it's kind of confusing because the carry itself is the advantage. So we only have to define one in a very weird way. So we have the last, the last advantage. And then what we pass here, we're going to pass a tuple. Let's leave that for now. Let's leave that for now. And we'll figure it out in a bit. So again, our advantage is equal to, let's look at it here. Yeah, if we look here, we have to compute the advantage estimates at each time step. So in a way, we want to save the advantages for each time step. And yeah, at each time step. And so if we look at the equation, this can be done recursively. Because, for example, in the first time step, this tells us how to get the final one, right? But if we want, for example, just the first time step, we don't care about this at time equals 1. We just care about this, right? So here's the first one, right? And then the second part, we can add this to the last advantage and then so on and so forth. That's actually what we're going to do here. So if we stare at the equation for a little bit, we look at what we're doing. We're passing a delta, right? And then we're multiplying times, we're doing plus gamma times lambda, which is another function we have to define. Now gamma, it was 0.99, right? Lambda, I saw papers doing it at 0.95. This balances like the variance. Let's just have it at that. Now this multiplies with, what does this multiply with? Delta, the future delta. In this case, that would just be the last advantage, which is what we have here. And don't forget, we have to put the mask on. And yeah, we multiply it by last advantage. And so we have to pass a delta and a done, 1 minus done here. Let's just kind of call it like delta and done. And by the way, what we return here is just return, and delta and done, it would be a tuple. So there you go. That's what we're passing through. Makes sense. Now looking back, right? Deltas, dones. Pass this through. Compute an advantage, and then we just pass the next advantage. We just pass an advantage, and then we return an advantage, and then we just return an advantage again. And we have to have 2 returns. This doesn't get like updated whatsoever, whatever. So we just pass it through, and then we get one of the advantages. It's the same thing, right? This is advantages, right? It's a list at this point. And what we do now is we calculate the returns. If you remember, the returns is calculated by the advantages, which is how much better it is, plus the values, which is what's predicted. And then here we just return advantages and the returns. This is just kind of a restructuring of that formula. Where is the formula? Right here, return minus critic, all that. This is just a restructuring of that, just simple algebra. Send the critic over to the other side, and then we find out that return is equal to advantage, I can't spell, plus the critic's prediction. Anyways, here you see that we have a return of the advantages and the returns. God, I hate the repetition of those words. But for each rollout, now we get to return stuff. So what do we return? Let's low-key just return everything for now. I'm not going to put much thought to it right now, but let's more or less just return everything that we have observed. So we return the observation, the actions, the rewards, the dones, the old log probs. This is important. Old log probs, right? Values, advantages, returns, and then everything that was taken out of the final carry. So here we have the final env state, and what is the last thing decoupled from the carry? Oh, the RNG. And yeah, I mean, that's pretty much our rollout function. Hope that made sense. Let's actually walk through it again. For a rollout, what we do is we define the number of steps in the rollout, and there we just we get 3 important values. Technically more, but we get 3 very important values. The actual action, not even 2. We get the log probs and the values. It's because these are what are going to be used anyways to calculate like the losses for our critic and our actor. And so calculates the advantage and all that. And so we save these 2 things. And then we also save the new observations and the rewards and all that, so that we can calculate the generalized advantage estimation, not generalized advantage equation, which I had to cut the video for. This is a little embarrassing here. But yeah, we're pretty much done with the rollout. After we roll out all of that, we have two things. We have the carry, but more importantly, we have the statistics, the buffer, the memory. And we use that to our advantage by saving the rewards and saving the dones and the values and literally everything, so we can compute the advantages backwards. Again, the reason we're doing it in reverse because we don't have, we want to start from where we know, which is where we left off, and go backwards. We don't want to infer like the first step had a reward of whatever. We just make our way back. And so our train step, how does our train step work? And I haven't defined what we pass through. Why haven't I? Well, we don't have our actor and our value, our critic yet. Let's straight up just get to work on that now. So let's do a models.py, and here let's import jax, import jax.numpy as JMP, and from Flax import NNX. So here we're going to make our policy model actor, and we're going to make our value critic. So let's start with our policy. Actually, it's just better to start with the critic model, pass nnx.module, and we're going to define the model. Now the model just needs an initial size, and a hidden size, and RNGs. Now, remember that this model outputs a scalar. It's just a scalar value, just defining the value at that specific state. So let's pass this for now. Right, let's create our two functions for that. And let's straight up just make a couple layers. I'm gonna do 3 layers just because that's what I did in the actual implementation. All our NNX.linear. Let me just make one and copy and paste it over for the other one. So the initial size is the initial size, then hidden size, because input layer, output layer, and then RNGs equals RNGs. And then let's kind of just copy that over here, except it goes from hidden size to hidden size, and then here it's the opposite. It goes from hidden size to 1, and RNGs is equal to RNGs. Now this RNGs stuff, I always like to put this, I don't even know the name of this thing, but it makes it so you have to write RNGs first. What's the name of this? Delimiter? What's the name? Hold on. What's the name of when I do a Python function and go like X, Y, Z? Please Google AI help me. Keyword only arguments. What's a delimiter? It's taking long. All right. You learned something new. And so this is called what? A keyword. Oh, okay. A keyword argument. Perfect. Yeah, this has to be a keyword argument. So you have to do RNGs equals whatever this is. Blah, blah. In this case, just RNGs. So then what would we pass? We just like relu, I guess. And then we just return self.fc3. Now this returns actually like this. We don't want that, so let's just squeeze it out. This returns just a scalar value. And so let's just copy this and make this the policy model. Initial sizes. Here we actually do need an output size. Reason being, we're not outputting just a scalar. We're actually outputting something. Yeah. Here we don't need to squeeze nothing. But as I said, let's have our sample. And our sample takes x and the key. And so we compute the logits first, right? This returns the logits of size like the output size. The output size would be like the action space. And then what do? We turn this into an action, right? jax.random.categorical. Cool. And using our key, we pass in our logits, and then our log probs, or log prob here is just our logits given our specific action. And what we want to return is action and log prob for that specific action. Perfect. And now we have to start talking, because now what's the reason I didn't start this? Oh, okay. We have to understand states and graphs, graph defs in JAX, especially with this new NNX module. Basically, I don't know how to explain this. We have to decouple what we pass through. Here, we have to do this thing called NNX.split. It basically splits the architecture. What is the architecture? Architecture is this, right? We have 3 linear layers, 3 forward layers, whatever. Output layer turns into a scalar, all that, you know, if you were doing a transformer, the attention mechanism, all that stuff, that is all architecture. And then the weights are something different. Since JAX is functional, we can't really pass the architecture through, and the weights shouldn't be attached with the architecture, right? We have to split them. I don't know if that was the best explanation, but I think it was a decent explanation. And so we have to merge. And so given our weights, we can't just, for example, here, we can't just output or do the sample or this critic stuff without the actual architecture. So what we have to do is this very like clever splitting and merging of the architecture with the weights throughout this process. So let's think about that now, right? Let's think about what we pass through our rollout. We pass our actor, the state of our actor, we pass the state of our value function, sorry, state of our critic function. And then here we have our initial observation, initial environmental state, and our RNG. Just pay attention to the syntax. But again, always imagine split the architecture from the weights, combine them when you need them, but keep the weights, the numbers, be what pass through our functional functions. So here we make an actor, and we do nnx.merge. We merge our graph def for our actor and our state for our actor. Now the graph def, I'm going to define it as a global variable. I still haven't found like the best approach to do that. You guys will see next week or in a couple days when I do my RLHF implementation that I pass graph defs as a tuple and then I pass the states as a tuple. I still haven't reached like a inner how can I call this? I haven't reached an inner consensus on how I want to approach this and how it's approached. I have to read a lot more code to build an intuition on what is correct. Right now, just imagine we have the graph def defined somewhere. And by the end of this, I'm going to print out all these things. Maybe it's a little bit more visual that way. But we do the same thing here, right? We make a critic, merge graph def critic, and then the state of the critic. Why was I making a big deal out of this? Well, we straight up just did the rollout function. But now for the train step, it's important to know that what we pass through is the state of the actor, the state of the critic, and then another thing that needs a state is the optimizer. So the optimizer of the actor, the optimizer of the critic, and yeah, we'll pass more things ahead. The whole point of this train step is for us to update the weights. Just a gradient descent step. But here we have two models, actor and critic. So first thing we're going to do is we're going to merge the splits. And we have to do two things, right? We have to merge the splits. We have to have the loss functions in here. And we have to gather the losses, grads, and using those gradients, we update weights, and then we return. Yeah. So then here, let's define our loss functions. We have two, right? Like I said, let's just loss. We have to define our loss functions. We have our actors loss function, which is which takes in the actor and other stuff. Pass on that. And then we have our critic loss function, which takes a critic. Pass on that. Let's do the critic. The critic is a lot more simple than the actual actor. First thing we want to do is we want to pass the critic, we want to pass the observations, and we want to pass the returns. Because the loss for the critic is nothing more than the separation between the value and the returns. So we want to return the mean of, it's straight up just an MSE, right? Values minus. Important here, we want to stop the gradients. We don't want the gradients to pass through the return. And then here, times 2. And this is another very important piece, right? Obs is now, it's n steps and 4, right? It's not 4 like it was in reinforce. So we're going to want to vmap this critic and obs. Yeah. That just computes a value for each observation. And will we just save this as values? And then for the actor, we do the same thing, right? We have to pass the observations, but we also want to pass the actions, the old log probs, and the advantages. Remember, the whole point of the advantages is to help our actor go in the right direction, right? So we Want to calculate some logits. Same thing, right? Our actor given our observation. And then we want to calculate the log probs. This is basically the same kind of code that we did in the sample function method. And here log probs. Oops. So we want to find the actual log probabilities of the actions that we took throughout this whole thing. And here is the important bit that we got from the paper. Where is it? We want to clip it, right? It's right here. This is the same formula that we're going to be implementing. We multiply by the advantages, right? We have this ratio, and then we have this clipped version of the ratio with a hyperparameter called epsilon. So ratio, let's just do the ratio first, right? Ratio. Now, what's the ratio? The ratio is the current log probability action distribution divided by the old log probs. Doesn't make sense why we're saving the old ones now. So the first thing we do is we a division between log probabilities, that is the same thing as a subtraction if both we put them to the power v. So jmp.exp, and what we do is the action log probs minus the old log probs. Now we also want to stop the gradients here. This is basically saying that we don't want gradients. We don't want any gradient updates for anything that computed old log probs. And then here we want to calc surrogates. What is that? That's basically this minimizing function right here, right? The minimum between this and this. And so we'll just do CPI and then clip. Yeah. So we'll just do CPI. What is CPI? It's just a normal ratio, right? Times the advantages. Again, we want to stop the gradients. Whoa. Advantages. And then we want to do the clip version. Now, clip is different, right? We want to jmp.clip. We want to do the ratio, but we want to do it between 1 minus epsilon, and then 1 plus epsilon. And then we multiply this same part. Does it make sense? We literally just copied the same thing. Clip, ratio, 1 minus, 1 plus. Same exact thing. Clip, ratio, 1 minus, 1 plus times the advantage. And here we just compute the loss, right? So the policy loss equals minus jmp.mean. And then we just put the minimum between the CPI and clip, the clipped version. And this is what we shall return. So yeah, we return both losses. Now, this is going to be an interesting thing. I wish I could explain it better, but fact of the matter is that it is not something that I knew, but just an issue that I ran into. And it has to do with the trace levels of JAX compilers. So I guess this isn't in the scope. Where are we? The actual loss functions. We can't just call actor loss function on whatever, because apparently these are two different levels in the compiler. Truth be told, again, I don't understand this that much, and I'll have to study more JAX for that for me to understand. But what we're basically doing here, though, I really wonder, and I think a good experiment would be just defining this inside of the train step. I think it has to do with how we merge our stuff. But anyways, we have to define an inner function here called a loss. And literally all you do is you just merge, you just return the actor loss function. And we have our actor. The parameters, by the way, are the graph depth, so the architecture of the actor with the parameters that we're passing through. And then it's just that. What do we need to pass for this? We have to pass the observations, the actions, the old log probs, and the advantages. So we already know what we have to have there, right? Obs, actions, old log probs, advantages. And how do I do? Yeah, whatever. One more thing. The loss function for the critic has the returns. So we're going to have to save the returns through as well. And that's that. So and we just do the same thing here. C loss params. Just call the critic NNX.merge the graph. Yeah. And return critic loss function for this. So then I guess if you want to do it at the same level, what we would do is we would define this here, but we would pass the state here and we would merge inside, I guess. Not too certain here. But it was an update that I had to make because my code would not run from that. And then we also want to merge the splits here. So we have actor. What is the actor? We just merge the graph def of actor with the state of the actor. The critic, what is that here? We want to merge the graph def of the critic with the state of the critic. And then same thing with our optimizers. So optimizer actor equals nnx.merge graph def opt a state opt a. And then optimizer for the critic, which is not the same, not merge. Now, if I'm being honest, by the time this video is already up, I've already done the RLHF implementation. Now, this was not working for me, having an optimizer as an Flax NNX like wrapped around that. It was not working for me. So I stuck with good old Optax, and so the code in the future might look a little different here. Might not be much merging here, but for now this worked well here, so I'm gonna just keep it. And we just want to gather the losses, right? And so the loss values for the actor, and then the gradients for the actor, which is returned by jax.value and grad. What we pass is the a-loss function with the state of the actor. Same thing here, right? We get the loss value and then the gradients value and grad, C loss, nnx.state critic. And so from that point, we just optimize, using the optimizer, we just optimize the actor with the new grads and then the critic with the new grads. And yeah, we're good there. So since we updated the actor, now the actor has a new state, right? So what we want to return is the new state of the actor, the new state of the critic, the new state of the optimizers, which get updated, and then the new state of the optimizer C. So you see how we're passing the state only? That's the same thing. So then for the next train step, we have a new state, and then we do a new update. And then what else do we pass? We just pass the same things through actions, old log probs, advantages, and returns. Oh, Wrong thing, sorry. Yeah, wrong thing, I'm so sorry. What we pass here, it would be the, yeah, we'd pass the loss values, sorry. We'd pass the loss values so that we could track whether there is improvement or not. And then for train all episodes, we have one train step here, right? There's another thing we have to do. We have to train an actual epoch, the PPO epoch. Remember, this is K epochs. This is just one step, but we want to do this K amount of times, right? This is just an update. And so here we have to make our train epoch function. Now the train epoch function pretty much takes the same thing. So you can straight up just copy this here, but here we call it train epoch. And what is this? This is just basically saying, okay, we're gonna do train step for K amount of times. And so you can see it's a very simple function, right? We just create a carry, an initial carry where we have the state of the actor, the state of the critic, the state of the optimizer, of both optimizers, and then we pass this through a body function, def body function, which I'm going to do something different here. I'm going to do this for a for I loop. So in here we're going to have I and we're going to have our carry. You're going to see the difference here. And so our final carry is basically going to contain like our updated states. But we're going to do this jax.lax for I loop, right? And where we're going to do this for between 0 and K epochs, which is going to be another hyperparameter, K epochs. Let's just put 4. A lot of the examples I've seen are 4. K 4 epochs. We're going to pass our body function in there with our initial carry. And that's just what we're going to return. And so look how simple this is, right? We're going to unpack our states, right? From our carry. By the way, 0 to K epochs, that's basically going to be this I. This I is only going to go up to K epochs. It's like a for loop. And then we take a train step, and then here we just pass all of this in here. A little boilerplate-ish, kind of bleh. That's how I feel writing all this. Get Cloud Code to do it for you. But no, especially stuff like this, like how lame it is to kind of write this down. But advantages and returns, right? Take a train step, and then we don't care about the losses too much here, right? But what we do care about is the updated states. Critic, state opt A, and state opt C. And yeah, we're pretty much done with that function. And so for train all episodes, this is where we do each and every step, right? So we're gonna have an initial environment reset. Whoa. Initial environment reset. Let's think about what we passed through. Probably just the states of the optimizers, opt C and RNG. right? Because here we create our environment, and so we do init, or we get our initial observation or initial environmental state from the actual environment, right? And then there's a key here, so let's just call it RNG reset, and we pass the params. If we have that, we already have our RNG here, right? So as I said before, we just split our key, and then we create our initial carry. Our initial carry, our initial carry will be kind of the same as our rollout. So here we define our init carry, and we are going to pass the state of the actor, the state of the critic, the state of opt A, state of opt C, the initial observation, the initial environmental state, and the RNG. And so we're going to receive a final carry and the rewards of the episode from a jax.lax.scan of a specific scan function. Now, this is the same thing as a body function. I kind of just like to name like the big final thing, just call it scan. I like the word scan better. It's like a personal thing. Just put body function there. We have our initial carry, none, and then we do this how many times? We do this for num rollouts. So how many rollouts are we going to do, right? We do that for a bunch, so we could do num rollouts. Make it like 16 or something right now, whatever. And so that's what we return. We're pretty much done with the thing, episode rewards, so you can keep track of your stuff. And so here we define the big final scary function, and then we're done. So we have carry. We unpack our states, right? Opt A state, opt C, obs, env state, and RNG. We get that from the carry. And we do the rollout. So what does rollout take? Well, rollout straight up just takes that. Again, rollout is what actually creates the stats that we end up using. So when we do the actor, the critic, and then we pass the observation, the environmental state, and the RNG. Now, what do we get returned from this? Let's actually do this on a different line because, oh God, this thing's going to be like a lot. But yeah. Let's see. Basically, again, this is what gets returned. See if this is simpler in any way. I think I would have been better off just. I think I'm gonna be better off just writing it down, right? So we pass our, make it into a tuple. Our observation for our batch. Again, our batch would be our rollout, our actions, our rewards, our dones, our old log probs, our values, our advantages, our returns, and then our next observation, our next environmental state, and our RNG. Perfect. And then we update the weights. So that's the rollout. Now we update the weights. The update weights part will be in the train epoch part, where we pass the state of the actor. We have it up here, the state of the critic, the state of the optimizers, the observations. Now the observations are for the specific batch, the actions, old log probs, one more, advantages, and the returns. And what do we get out of this? We get just the updated states for all these things. So there was no need for me to do this, so forget about this. Yeah, I mean, we get that out. And then we create our carry for the next step, which is just the state of the actor, the new state of the actor, the new state of the critic, the new state of the optimizers, and then the next observation, the next environmental state, and our RNG. We just calculate an average episode reward here. This will be its own function. Honestly, this code here, I'm gonna copy and paste it from my implementation, and I'll explain it. This, again, we're calculating the returns. We are disregarding wherever done's is a 1, which means that episode's done there. We don't calculate a reward for that. That's basically it, what we do here. Then we do this for the amount of episodes. We calculate the mean reward. That's kind of just what we pass through here. We pass the rewards and the dones. Here, compute mean episode reward, rewards, dones. And yeah, that's PPO. You coded it all from scratch, right? The most important bits. And now I'm going to basically show how you end up testing it. And a lot of the things are going to be more clear now, right? So here we just do our main function. And I want to import time because this is very interesting for me, seeing how quick things are and also how much JIT takes to compile the first epoch of things, the first run of things. Anyways, for something like this to run, first thing you want to work on is the keys, the RNG. We're going to name a random RNG. This is the way to do it, jax.random.prng key. I like 42. Just put whatever number there. And then we want to initialize models and parameters and optimizers, sorry. So our actor is equal to our actor model. Now this is something we have to pass through. And I'll name a couple other hyperparameters. So the way this works, let's go all the way up here. From .models, import actor model and the critic model. And let's name a couple other things. The observation size, if you guys remember from the other implementation, is 4. The action size is 2. You could either go left or right. Hidden is equal to 128. These are just things I have. And then learning rate, I'm just going to do, these are all, I think, pretty sure same number from, what's it called? From the reinforced implementation. And yeah, we should be good with this. Oh, epsilon. I forgot to name epsilon. That's 0.2, just like from the paper. Go all the way down. And first thing we want to do, we want to initialize this. So the initial space is the observation size. Then we have hidden, and then we have action size. And then remember, RNGs equals RNGs. Not the delimiter, but the keyword argument. Critic is the same as the critic model. And here we pass the observation size and hidden, but we don't have an output because the output's just 1. RNGs equals RNGs. And then we have to do the same thing for the optimizers. Here I'm wrapping it in like NNX.optimizer. That's not something I'm doing from now on going forth. And we declare our optimizer, which will be atom, with respect to NNX.param. Same thing with the optimizer for the critic. Critic optax.atom learning rate, and then with respect to the param. And then we do the splits here, right? And also RNGs is equal to, we have to wrap it in NNX.RNGs. Now the split here, this is graph.def actor, state actor. This is how you do it. It goes NNX.split actor. We do this throughout. And this is a lot of boilerplate. I have to sit there and think a little bit on how I can make this process a lot more efficient. But yeah, I mean, for now, let's take my current skill level. This is what we got. So we just define all of these and we split them, right? And so now we want to begin training. I want to declare a time. Like I said, one of my wonders is like, well, let's see how fast this is. And what we're going to do is we're going to train all episodes. And we're going to do this for the state of the actors, the state of the critic. These are, remember, the things we passed through. State opt C. You can see it up there from our last function, train all episodes. And then RNG. I'm going to split it to RNG train. RNG train. You guys should already know how to do this part. jax.random.split RNG into 2. And so what do we get returned out of that? We just get, I believe, a final carry. Yeah, and the episode rewards. And yeah, time taken. How much time did we take? Minus T0. And yeah, I mean, that's pretty much how we test this out. Let's print the time taken. Let's print the episode rewards, the first 10 of them, and then the last 10, and see if our model had learned something throughout its steps. We should be good to train, right? So now go to your terminal. Am I supposed to have anything installed? I think you should be good. If it asks you to install anything, just install the dependencies. Python-m PPO. Whoa. Okay. Yeah. You see, I have to do some of the imports. I should probably edit this part out because I do be forgetting my imports. Another error, I passed the length of action inside of the loss function for the actor. Here, where are we at? Actions. There is no action in the scope anyways. Let's see this. Another error, stop gradient, not stop gradients. I got the whole API wrong for you guys. I'm sorry, gang. It should be it there. A lot of errors at the end, man. Okay. Let's debug this. Body function init carry. Okay. The input component loop. The scan body and input must have the same structure. Yeah. Yeah, I completely forgot to return anything there. Yeah. You just return the same things. Make sure to always return the same things that you pass in for your opsi. Should be good. Forgot the minus here. Bang. Ah. Oh my god. Damn. So it compiled in 1 second. And yeah, I mean, you see improvements. There may be some bugs maybe throughout the code, but you do see improvements. The maximum we can have is 128 since that's the length of our rollout. We achieved it multiple times. It's basically solved by that point. There is some variance here with this 8, but overall you just built a PPO for CartPole. Very primitive like implementation of it, or not a primitive implementation, but for a primitive environment. But this is basically PPO in all its glory. Next video, wait, let me do something cool. Next video, we are going to read Instruct GPT and a bunch of other RLHF papers that basically set the foundation to how these models became so smart and human-like, not just very good at interpreting and decoding language, but also just the feel of human. How does it feel like I'm talking to a person? How can it help me really well? We're going to go over specific structural choices that they made using PPO. And then for the video after that one, we are going to implement a whole RLHF pipeline from scratch in JAX. But this video sets a good foundation for that. And now we're way past foundational stuff. This is straight up PPO from scratch. But RLHF is a lot more complex. And we're going to talk about it. We're going to see why that is an issue. And then that just sets the path for the future of the series. So thank you guys so much for watching. I really appreciate you guys sitting through all hour and a half of this or whatever. And I'll see you guys soon.